We'll be starting with a brief introduction to the inverse design method and discuss the problem statement. Then we'll be looking at how the rotor of the radial inflow turbine can be designed using the 3D inverse design approach. Then we'll move to how the efficiency of the rotor can be enhanced while ensuring structural integrity through the use of automatic optimization with inverse design. And of course, we'll evaluate the aerodynamic and mechanical performance of the turbine based on CFD and FEA analysis. And finally, we'll wrap up with some concluding remarks. So let's start with an introduction to the idea behind the inverse design approach, which we use throughout the project. And you can see in this workflow, these are the inputs that are used by the inverse design method to give us the final blade design. So apart from some basic parameters, the blade loading inputs are really flow related. And so once you have a good understanding of your specific flow issue, whether it's profile loss, secondary flow, or shocks that you are dealing with, it's possible to come up with guidelines on the optimum blade loading to tackle each of these issues. And actually, this know-how has generality, which makes it suitable for all your turbine applications. And what's interesting is that you only need to rely on your knowledge of flow physics, and then this method works for you, regardless of your turbine size or which specific speed regime it falls under. And this makes the entire process very intuitive and removes any empiricism that's commonly seen with conventional design methods. So let's look at the design of turbines in a bit more detail. So across the specific speed range, turbines are subject to various flow phenomena and loss mechanisms which are dominant in that particular range. For example, as you can see in this specific speed chart, leakage and secondary flow effects are more dominant in the lower ranges, whereas shocks and profile losses take priority in the higher ranges. And in fact, with inverse design, it's possible to come up with a set of optimum design guidelines based on these fluid dynamic considerations of reducing the dominant flow losses in your turbine. And this is actually what we aim to explore through this webinar. However, when it comes to high-speed turbines, there is usually a trade-off between the aerodynamic and structural aspects of the rotor. And this brings us to our problem statement. Now, in case of high-speed radial turbines, like those used in turbochargers, they operate under a very demanding environment. And so it's a common practice to use modifications like radial filament. But while this reduces the stress levels in the rotor, making the operation safer, it also takes a heavy toll on its efficiency. And that's why in a previous paper, we used an inverse design based approach involving multiple CFD and FEA runs in order to ensure that the appropriate trade-off was achieved, where the designs were purely radial filament due to some post-modification on the 3D geometry. And this did result in a highly optimized design with a high efficiency and stress levels that were well within the material strength. And so we are going to refer to this as the baseline design for reference and for comparison in the present study. However, despite being highly effective, such an approach can still consume a lot of computational time and resources. So the question is whether it's possible to come up with a rapid optimization methodology which can match the performance levels of computationally expensive methods while still avoiding a large number of CFD and FEA runs, and also avoiding the radial filament modification. And this is what we aim to explore through this webinar. And in fact, this is based on one of ADT's technical papers that was presented at the 15th IMECI Turbocharger Conference in 2023 last year. And so to put things in perspective first, here is the previous optimization workflow and how it compares to the present one. So while the previous study started from an initial design and took several weeks to complete using multiple CFD and FEA runs and achieved an optimized design, which we are going to refer to as a baseline here, the present approach goes from the initial design straight to TD1 optimization, which is much quicker and still results in an equivalent performance to the baseline. And of course, some CFD and FEA is performed, but this is only to validate the final design.